All right, so the first thing that I want to talk about is what a field force is, because this lecture is all about electric fields. So what do we mean by a field? So a field force is a force that can act with no physical contact. And if you think about it, can gravity do that? Can gravity act with no physical contact? Like, here's the Earth. You know, if you put an object above the surface of the Earth, what's the Earth going to do to that object? Pull it down. There's going to be a force there, right? No physical contact. That's why we call it the gravitational field. Can charges do that? You know, here we have a big negative charge. If I stick a positive charge right here, can this big negative charge exert a force on the little positive charge? Yeah. Any physical contact there? Nope. So it's a field force, right? And just so we're clear here, you know, these masses, the Earth and this little mass, they're exerting force on each other. You know, so if I were to like erase here, is the Earth being pulled up towards that little mass? Yeah, it's a mutual force, right? Is this charge, is the big negative guy being pulled towards the little positive guy? Yeah, every force has an equal and opposite force. And that's what we talked about yesterday, you know, finding the force between objects and the force between charges. What's the equation for finding force between two masses? So we'll call this guy M1, we'll call the Earth M2, the distance from center to center is R. What's the equation here? Big G, M1, M2 over R squared. How about if it's two charges? So we'll call this guy charge 1, we'll call the little guy charge 2. You know, the distance between them is R. What's the equation for finding that force? K, Q1, Q2 over R squared. So you should recognize that these two equations here, they're basically the same equation, right? They're basically the same. All right, so today we're talking about electric fields, and the way I like to teach this is by starting out by reviewing the gravitational field, which you already know a lot about from first semester. So which way does the Earth's gravitational field go? I hope you know this. It goes straight down to the center of the Earth, right? So these arrows that I'm drawing here, these arrows represent the Earth's gravitational field. So we'll just label it with a little g. Now, what if you put a mass near the surface of the Earth, or even not near the surface of the Earth? What will the Earth's gravitational field do to a little mass placed in the field? It'll pull it down, right? So this little mass here, which I'll label this guy little m, and then the Earth will be big M. The Earth is big M, that mass is little m. In first semester, we learned the equation for force of gravity. It's like one of the very first equations you learned in this class. What's the equation for force of gravity, also known as weight? Mg, where that's little m, right? Little mg. So that's the first equation I have down here. So this should be totally familiar to you. The equation for gravitational force equals the mass of the object in the field multiplied by the gravitational field at that point, right? Okay, now what's this second equation all about? You may not remember it, but we did this with Newton's law of gravitation. If you travel from the center of the Earth, so we always measure distances center to center, from the center of the Earth, if you go out to a point, you can calculate what the gravitational field is there. Is it going to be 9.8? No, not if you're way above the surface of the Earth, it won't be 9.8. The equation for finding the gravitational field at a point on or above a planet or a moon or an asteroid is big G, the gravitational constant, times m. Notice that's big M, not little m. Big G m over R squared. So that's our second equation down here. And real quickly, I'll show you how you could figure that out. If you stick little m, so just for a minute here, just put little m at that point. Little m is attracted to big M, and big M is attracted to little m. But what is this force right there? That force, we have two equations for it, right? What are the two equations for that force? You could say little mg, but then what else could you say? Big G, big M, little m over r squared. And then the little m cancels, right? Then you're left with that equation, G equals gm over r squared, okay? Now, so these are the equations that you already know for the gravitational field. Now, let's look at the electric field. So here we have a big negative charge. Is there a field around that big negative charge? There is, because, you know, when I say there's a field around the big negative charge, all I mean is if we put a little positive charge, for example, if we stick a little positive guy here, is that little positive guy going to get a force? Yeah, it's super similar to this guy, right? The little m right there. Okay, for right now, I'm just going to tell you which way the electric field is for this situation. And in about 5 minutes, I'm going to talk about the direction of electric fields. So in this situation, the electric field goes in to the big negative. So this arrow represents the electric field. So these arrows here, actually take that away. These arrows here are represent the electric field around the big negative guy. Now, if we stick a little positive guy in this electric field, put a little positive guy in the electric field, would that little positive guy get a force from the electric field? Yeah, it's the same thing as this little mass in the gravitational field. So the first thing I want to teach you is how to calculate the force of an electric field. The equation for the force of an electric field is QE. So this is going to be Q, and then I'm going to make the big guy capital Q, right? Just like with over here, it was little m, big M, we're going to go little q, big Q. So the first equation on our list is force of electric field equals QE. I put that as Q naught. Okay? Now look, I want you to recognize something, because this is going to help you understand it. Notice that the equation for the force of gravity and the equation for force of an electric field, notice that they are the same equation. What do gravitational fields care about, charge or mass? Mass. So we have mass here. What do electric fields care about? Charge. So look, the M becomes Q and the G becomes E. They even sound the same. mg, QE. mg, QE. Did you hear about my song? I wrote a song about this. It's kind of a rap song. It goes like this. It goes mg, QE. You guys like that song? Yeah. Hey man, that's such a good song, dude. Hey, you know what? Honestly, if I whip my hair back and forth, it's on the radio, I don't see why that couldn't be. I whip my hair back and forth. I whip my hair back and I whip my hair. MG. QE. I call it. Dude, I just did record that. That's going to be online for people to make fun of me about. It's called the MGQE song. MGQE. Okay, I'm trying to drill it into your head. All right. Huh? My road to stardom. I thought you said stardom. I'm like, my road to stardom. Okay. Now, second thing. Look, this is getting messy, but look, we can do it. Look it. If you want to find the electric field at a distance from a big charge, right? So like you travel a distance r away from the big charge, and you want to calculate the electric field at that point. Dudes and dudettes, notice that this second equation is the same as the equation we would use in a gravitational field problem. right? The big G becomes what? The gravitational constant becomes the Coulomb constant, and then big M becomes big Q. Does that make sense? It's the same equation. You go K, Q over R squared. That is how you calculate the electric field at a distance from a big guy. Okay, so let me revert this, clean it up. So these two equations are identical. You know, one's for mass, the other one's for charge. And then these two equations are identical. Now notice I was saying big guy, little guy. In this class I talk about big dude and little dude. The College Board will not use that terminology. Okay, they're not going to be like, hey bro, so the big dude has a charge of 8 microcoulombs. The College Board and the textbook, the proper term for big dude is point charge. And then the proper term for little dude is test charge. So point charge, you know, I typically go big Q and then little q. Very frequently, the little dude is Q naught. If you see a Q naught, that's little guy. Yo.
Does the absolute value just mean you want all the charges to be positive?
In here? Yeah, when you plug into this equation, don't worry about sign convention. The equation is not going to tell you the direction of the electric field. So the next thing I'm going to talk about is the direction of the electric field. Okay? All right, so at this point, look, I like to personalize gravitational fields and electric fields. Wake up. You. Yeah, wake up. This is good stuff, man. Okay. Say you go to a party. When you go to a party, or I should say when grown-ups go to a party, what's the number one thing they talk about? Like when you meet somebody new. What do you do? Hey, man, what do you do? And I'm proud to say that I teach physics, and they're like this. People are like, physics? That's awesome. And I'm like, yeah, it is. It's way awesome, okay? So anyway, I want you to imagine that you go to a party and you happen to meet Mr. Gravitational Field. And then the topic comes up of like, hey, what do you do? What would Mr. Gravitational Field tell you? I exert force on anything with mass. That's what the gravitational field does. Anything with mass gets a force, right? Gravitational field, boom, 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 around the Earth. Anything with mass in that field gets a force, okay? Now, you go to a party and you meet Mrs. Electric Field. Now, I purposely made one male and the other female on purpose, so I'll tell you why. Now, you meet Mrs. Electric Field, okay? Now, what would Mrs. Electric Field tell you? So here she is right here, Mrs. Electric Field. What would Mrs. Electric Field tell you? She exerts force on anything with what? Charge, okay? Now, why did I make one male and the other one female? And I don't mean, you know, I don't want to be sexist here or anything, but science has shown who's a little more complicated. Not dramatically more complicated, but a little bit more complicated. Guys or girls? No, girls. I'll be serious. Hey, science has shown like the way the female mind works. It's not what's the word I'm looking for? Like when dudes have thoughts, it's very compartmentalized. It's like I am thinking about homework. I am thinking about food. I am thinking about sports. You know, it's like very compartmentalized, and they've shown the female brain is not compartmentalized like that. Have you guys, who's heard this before? In biology, or you've heard this? Yeah, the way women think, it's more like everything kind of connects together. It's not in little boxes. So, hey, I don't want to offend any girls in here. I kind of mean it as a compliment. It's more interesting to be complex. But look, of the two, look at gravitational field or electric field. Which one is slightly more complicated? The electric field, and I'm going to explain why. Ready? So here is why the electric field shall be feminine. A little more complicated. If you think about it, here's the problem. Look, if you put a positive charge near this big dude, right? Oh, and by the way, what do I mean by big dude? I've been saying big dude, little dude. Just so we're clear, the big dude is the creator of the field. The little dude goes into the field. That's the difference between big dude, little dude. Point charge, test charge. All right, if you put a little guy near a big negative, which way does the little positive guy want to go? Towards, right? Okay, now what if we put a little negative near the big negative? He wants to go away. So this presents a problem. Which way is the electric field going to be? Is the electric field going to be this way, or is the electric field going to be this way? The answer is everything is based on little positive charges. And that's true for the whole semester, not just for this chapter. You know, later on when we get to electricity, guys, what actually is electricity? Is it positive charge motion or negative charge motion for real? Like, here's a wire right here. Which way, what moves through a wire? Electrons, which are negative, right? But guess what? In physics, how are we going to define charge motion in electricity? Positive charge motion. Even though, in reality, what's moving? Negative charges. Doesn't matter. Everything in physics is based on the little positive charge. Okay? So, here's what that means. Here's what that means. We have a big positive dude. We have a big negative dude. Okay? The electric field for a big positive, which way does it go? In or out? Out. Why is that? If you put a little positive guy near the big positive, which way is the little positive guy going to go? Out. That's the direction of the electric field. The direction of the electric field, so these arrows that I'm drawing, these arrows represent the electric field. The direction of the electric field is simply the direction that a little positive guy wants to go when placed in the field. So if you stick a little positive guy right here, which way does he want to go? He wants to go that way. That's the direction of the electric field. If you stick a little positive guy right here, which way does he want to go? That way. How about right here? That way. Okay, now let's go to the big negative. Ready? If you look at the big negative, which way is the electric field for a big negative? Well, if you stick a little positive guy right here, which way does that little positive guy want to go? In, 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 all the way around like that. So in general, electric fields go out of big positive and in to big negative. Does that make sense? Okay. Another way to put this, and this is important, guys, this is super duper important. Little positives want to move which way? With the field or against? Little positives, with the field or against? With, because that's how we define the field. The field is defined based on the little positive. Little negatives, so let's put a little negative in here. Which way do little negatives want to go? Against the field. Little negatives move against the field. Little positives move with the field. Does that make sense? Okay, now let's go to our problem here. All right, so this problem, I actually have a video solution posted for it, but I want you guys to start it right now. The first question, so, well, you got three charges here. We're going to say that this charge, I'm calling this guy number 1, this guy's number 2, and this guy's number 3. The first question is, find the total electric field at this point right here. What is the total electric field at this point? Now, guys, you need to accept sooner rather than later that this chapter is highly tedious and highly, you know, a lot of calculate this, calculate that, a lot of big numbers. So it's gonna make you work, okay? All right. How many charges are contributing to this electric field? Just one or multiple? Multiple. All three of these charges, this guy, and this guy, they are all contributing to the total electric field at that point. Okay? So the first thing we have to do is figure out the direction of the electric fields at this point. Okay, so let's start with charge 1. So is charge 1 plus or minus? Plus. What do we know about the electric field for big positive? Goes out in all directions. In all directions the electric field goes out. So those arrows are the electric field. But what's the electric field from charge 1 doing over here? At the point that we're focusing on, isn't the electric field going like this? Bam, like that. We'll label that E1. That's the electric field for charge 1. At this point right here, the electric field from charge 1 points directly to the right. Okay? Now let's go to charge 2. Is charge 2 plus or minus? Plus. So what do we know about the electric field for big positives? Out. Out. And why is that? Why is it out? Because that's what a little positive would do. You got to remember, these 3 charges in this problem, these are big dudes. These guys are big dudes. In this problem, they're creating the electric field. Now, what's the electric field from charge 2 doing at the point we're focusing on? It's going like this. Ready? It's going out, 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 out. Bam! Like that. E2. So I'm just going to go like this. Just go like that. E2. So that's what electric field 2 is doing. Now, charge 3 is negative. The electric field for negative charges go in, like this. In all directions. But what's that electric field from charge 3 doing at the point we're focusing on? It's going down like that, right? So that's E3. So pretty much here is our situation. You're going to need to solve for this theta right there. You need that theta. How are you going to get that theta? Well, it's the same as this theta. So get it from the triangle. Okay. Next thing. We have to calculate E1, E2, and E3. How do you calculate the electric field? Well, what's the equation for the electric field from a big guy? What's the equation you're going to use for those 3 calculations? KQ over R squared. Okay? So find out what those electric fields are. Are you done yet? No. This chapter is tedious. It is. Once you've found what those electric fields are, I got my vectors out here, you need to figure out what is your total x, which is going to point somewhere that way. What is your total y? Put them tip to tail, and then the answer you're looking for will be the hypotenuse. Okay? So it's definitely, it's an exercise. It's multi-step. All right, any questions on this? Okay, so watch the video solution. That's it.